Okay, so we are talking about the elimination method in 6.2, and this is another method, another way that we can break down trying to solve systems of equations. We did the substitution method last time. Now we're talking about the elimination method. So let's take, for example, this system that we have here. I have 3x plus 2y equals 4, and I have a 5x minus a 2y equals a 12. Anybody notice anything nice about this one? Amy, what do you notice there? There's a positive 2i and there's a negative 2i, okay? And this is actually really, really nice for us because look what would happen if we added these things vertically. This is a very, very basic example to get the point across, okay? If we added vertically, notice that my x's line up vertically, my y's line up vertically, and then my numbers line up vertically. So if I added vertically, look how I'd get this. I'd get 8x is equal to 16 because 2y minus 2y, that cancels out. And look, the y has been eliminated, right? That's the whole point of why they call it the elimination method. So the y has been eliminated, so therefore we can go ahead and solve for x. So I'm going to divide by 8 on both sides. Looks like I'm getting x as a value of, everybody? 2. Very good. Thank you. So now if x is 2, I'm going to take that 2, I'm going to substitute it right back in for any x value that I had. So 3 times a 2 plus a 2y, it's got to be a 4. So 2y has to be 4 take away 6. What would that be? Negative 2, so y has to be negative 1. So therefore, my solution would have to be 2 comma negative 1. All right, everybody, try this one on your own. This is a real basic example, and then I'm going to kick it up a notch and try something different with you. So right now, you try this one on your own. X plus 2y equals 6, and x minus 2y equals 2. Try the elimination method and see what you get. All right, so solving this, most people in the room did get the right answer of 4 comma 1. So I'm feeling pretty confident now that you've got the elimination, the basic one under control, right? But what happens when we make it a little bit more challenging? What happens when we have something that looks like this? So for example, let's say we have this system. Let's say we have 2x minus 4y is equal to negative 7, and 5x plus y is equal to negative 1. All right, this one's a little bit different. I wonder if you notice what's different about it. Yeah. And what do we call the numbers right in front of the coefficients, everybody? Oh, shoot. What do we call the numbers right in front of the variables, I mean? Coefficient. Okay, so there's no coefficient that have the same value. But notice that the x coefficients, those are both positive, right? The y coefficients have opposite signs. So we're looking for the ones that have opposite signs because we want to add these together. Nelson, what do you see, dude?
Oh, like you can multiply the entire bottom equation by 4.
Yeah, that's a great idea. So Nelson says, okay, he's noticing that we can multiply this entire bottom equation by a value of 4. Nelson, why did you pick 4? I'm curious. Why'd you do that?
Because you get a positive 4y, and then they'll cancel out.
All right, good. So if I rewrite everything, I'm going to have 2x minus 4y equals negative 7. And if I distribute my 4 in, I'm going to get, what was that, 20x, yeah? Plus 4y is now equal to a negative 4. Everybody cool with that part?
Yep.
Okay, now you notice that the y's are set up to be eliminated. So that means that I've got 22x when I add vertically, 4y and negative 4y that go away, is equal to negative 11. Therefore, dividing by 22 on both sides, I'm getting that x is a value of what, negative 1/2? You guys cool with that? All right, so if x is negative 1/2, we're going to go back in here. We're going to substitute back in. And we're going to get 2 times negative 1/2 minus 4y has to be a negative 7. So negative 4y has to be, let's see here. Well, 2 times negative 1/2 is negative 1. If I add 1 to both sides, I get 6, right? So I would get on the other side, yeah, what would I get? I get a negative 6, right? I heard 6 out there. So that means that y has to be what value? 3/2. So therefore, the solution to my system will be negative 1/2 comma 3/2. You guys think about that? Is that true?
Yeah.
Okay, good. So here's what I'd like you to do. I'm wondering if over to the right, could we write down some of the steps that we just did? Think about that with your table group for 1 second, okay?
Yeah.
Okay, what'd you do?
First we found like if the variable that has opposite signs,
Mm-hmm.
and then we
So you basically just choose a variable,
yeah
okay?
alter it to have the
Ah.
balance of the coefficients.
Good. Get matching coefficients. So yeah, then you basically solve, right?
Yeah, you solve this equation.
Okay. And then how do we get this second one out of here? How do you get this?
You plug in what you get.
Yeah.
And
Back substitute. Good. So check it out. Those are the steps, right? We picked a variable. We figured out how to get matching coefficients. We solved it. Then we did back substitution. And then our last find that we could actually check on the calculator to make sure that we did it right. Okay, so there's some 5 basic steps that we could do. What do you guys think about that? Pretty good? Yeah? All right. All right, so we now know how to algebraically eliminate equations or eliminate variables and solve systems of equations, okay? So the other thing that we can do is we can solve these on the graphing calculator, which is what I want to explore with you right now. Now notice that the 5 and the 2, they're different numbers. They're the same sign. For my coefficient for the y, I have a 3 and a negative 4. So I would have to multiply the top equation by what number, you guys?
4.
By 4, and the bottom equation by what number?
3.
By 3. So we could take that route. We could definitely do that, right? Okay, but instead what I want to do is I want to solve it on the graphing calculator. In order to solve it on the graphing calculator, I need to isolate y. So right now in your table groups, could you please isolate y for me in both the top and bottom equation? All right, Bobby, could you give us the first one, please, buddy?
9 minus 5x over 3. What?
9.
Wait.
Yeah, so he did 9 minus 5x over 3.
Oh yeah.
Is that okay? Is that right?
Yeah.
Yeah, we take that, right? Okay, good. Can someone give me the second one?
That's a strong word.
Nelson, give me the second one.
1/2 x minus 7 halves.
1/2 x minus 7 halves. That is correct. Did it make anything different? Or 2x, yeah, minus 14 divided by negative 4. Also, that will work, okay? All right, so ladies and gentlemen, get your calculators out, please. We're going to go to y equals, and we're going to clear everything out of here. We need to plug into our calculator exactly the equations that we have here, because now we've isolated y. I want you to have this skill on the calculator. Who does not have a calculator? Raise your hands, please. Good, everyone has one. Awesome, great. Grant, where's yours? Okay, all right, let's plug in the top. Now, you need to plug it in the calculator with the numerator in parentheses so that the calculator doesn't get the order of operations mixed up. So as an example like this, parentheses, 9 minus 5x. All right, close parentheses, and then divided by the number 3. That's how you match what you've written over here. 9 minus 5x divided by 3. Looks like that. All right, then the second one. This one is 1/2 x, so I'm going to go 0.5x. Oops, I pushed 8. 0.5x minus 7 divided by 2 is 3.5, right?
Yeah.
Okay, so I'm going to do it that way. So however you have it, you're good to go. All right, then from here, we're going to hit zoom 6. Everybody hit zoom 6. Take a little calculator selfie. Does that look like yours? Calculator selfies. Good. So yours looks like mine. It's all good. We're all good to go. Okay, great. So we're going to do intersection. Second, calculate. And we're going to go to option number 5. This is just like the quick start today. It's asking you for the first curve. So I'm already on one, so push enter. Automatically jumps to the second curve. Push enter again. And then it should give you the intersection at the point 3, negative 2. Awesome. Therefore, we can solve this system by saying the solution is at the point 3, negative 2. So I have 3 sets of systems equations. I have set A, set B, and set C. I want the guys right here in the front, I want you guys to take set A. In the back there, in the middle room, I want you guys to take set B. And then ladies up here in the front, I'd like you to take set C. And what I want you to do is I want you to graph each system in your graphing calculator and discuss the graph that you see. Okay, so graph each system in the graphing calculator and discuss the graph that you see. That's your task right now. Please do that. Gentlemen, you had this system in the front, right? You had 2x minus 3y equals 3, and then you had a negative 4x plus a 6y equals 6. So when you graph this, guys, what did you see?
We saw parallel lines.
And so you saw 2 parallel lines. So you saw something that looks like this, right? Okay, what does this mean?
That
Interpret.
The slope is the same, but the x-intercepts in this case are different.
Okay, the slopes are the same, but the x-intercepts in this case are different.
They
All right,
don't
and
intersect.
and the lines never intersect. So do you guys agree with that part so far? Is that cool? So I'm gonna put this with this graph here. Is that good?
There's no solution to the system.
So you say there's no solution to the system. Why do you say that?
Because the solution to the system of equations is the intersecting point, and there's no intersecting.
So you say it has to intersect in order to have a solution, and there's no intersecting point here. So therefore, there's no solution. Okay, that's interesting. Okay, I like it. Okay, in the back there, when you guys had 2x minus 3y equals 3, and then x plus 2y equals 5, right? What did you see when you graphed it?
It intersects at 3, 1.
So it intersects over here, some point 3, 1, right? If we zoom in, right? That looks like 3, 1. If I go, yep, look, there it is right there. Okay, so talk about that one for me real quick.
I thought that when you graphed it proportionally,
Yep.
it formed about a 25 by 155 degree angle.
Oh, you actually went in and calculated these angles. Okay, that's cool. But in terms of the system, what could you say about it? What could you say in terms of the system? Two linear graphs, yeah, but these are also two linear graphs. What's the difference between these two? These intersect, right? So how many solutions would you say it has? All right, fair enough, fair enough. Okay, and then girls, up front here, what did you see when you graphed this system? Yeah, so look, check this out. This looks like only one line, but in fact there are two that are graphs. So what do you think this means?
They have the same line.
They're the same. What do you mean by yeah, they are the same line, right?
The same values.
Same values here. Okay. All right. So it turns out, you guys, that these two systems over here, there's a name for all these. That's what we're going to talk about right now. Okay. These two systems over here, these are what's called consistent. Consistent systems. Consistent, like consistent. So those two are consistent because they have answers, right? This one over here, this is called an inconsistent.
Take care, I still love the way you are.
Okay? So now, there's two different types of consistent systems, okay? If a consistent system with infinitely many solutions, that's the one on the far right, that's called a dependent system. Okay? A consistent system with only one solution is called an independent system. So you might want to take note of these names here. So independent, dependent for consistent systems. Okay, now here's what I would like you to do. Yes, sir?
What about if it has two?
Okay, here's what I'd like you to do. In your table groups, all right, I'd actually like you to solve these algebraically. Solve them algebraically and see what you get when you solve them algebraically. Let me shrink this down a little bit so we can talk about that. So we have them solve them algebraically. So, gentlemen in the front, what'd you come up with when you did your inconsistent system with parallel lines? What'd you get for the algebra part?
So when we multiplied the top by 2
Uh-huh.
to do the elimination
Yep.
method,
Yep.
it came out as 4x minus 6y equals 6, and then all the numbers with variables canceled, so it turned into 0 equals 12.
Yes, very good. Okay, so check this out. When you are solving algebraically using elimination or substitution, and you come across what's known as a false statement, right? This is totally false. A false statement in the algebra is telling that there is an inconsistent system going on, meaning that your graph will be parallel, meaning that there's no solution to this, right? So in this one, we can say then finally there is no solution because, ladies and gentlemen, we are getting a false statement. So I want you to be able to connect the algebra to the graph. That's the whole point, okay? Group B, what did you come up with when you found what you got there?
We get x equals 3 and y.
Yeah, you got 3, 1, which means there's only one solution, right? So, ladies and gentlemen, If you're doing the algebra and you come up with one solution, that means you have an independent system, and there's one point only on the graph that works, okay? So you should get like a normal equation, right? But girls, what did you come up with when you found yours?
0 equals 0.
Yeah, you got 0 equals 0, or you'll get something like 5 equals 5. So you'll get what's known as a true statement. Okay, if you get a true statement, then that means there are infinitely many solutions. So my goal for box number 5 is for you to be able to relate the algebra with the graph and tell me whether or not it's inconsistent, consistent, dependent or independent, one solution, no solution, or infinitely many solutions.